Hi folks, today in this video we're going to try to answer a question that I've been asked quite a bit in the last couple of days. And that question is, why factor? So let's take a look at an example here. Say I have a polynomial x squared minus 6x, and I ask you to factor this polynomial. So we recall that we do this by looking for a common factor, a factor that is included in both of the two terms of the polynomial. And we look at this here and we realize that the common factor is x. They both possess a factor of x, so we can write this as x times, and what we're left with here, once we take out one of the x's, we're left with the other factor of x. And here, when I take out the factor of x, I'm just left with the minus 6. Okay, and we can do a quick check. X times x squared, x times negative 6, negative 6x. So we've managed to write this polynomial as the product of two other polynomials. So we've factored it. The question is, why do we do this? You'd almost say that this expression here was actually the simpler one of the two. So why in the world would you write something in a more complicated way? So that's what we're going to try to answer today. We need to take a couple of steps back, though, before we can answer this question. And I want to start by going back and looking at solving simple linear equations. So say I have something like 2x minus 7 equals 15. So we recall that we solve this by using opposite operations and by doing the reverse order of bed mass in order to isolate the x. So first I take care of the minus 7. So 2x equals, bring it to the other side, 15 plus 7, so 22. And then here we can divide both sides by 2, the opposite of multiplying by 2, to get x equals 11 as our answer. Now we can actually apply this method, and we have, especially when we were working with Pythagoras, on some non-linear equations. So in particular, if I have 2x squared minus 32 equals 0, say, okay, so let's try to solve using opposite operations. So we'll start with the minus 32, bring that to the other side. We have 2x squared equals positive 32. Next, we would take care of the multiplication. So x squared, divide both sides by 2, equals 16. And then finally, we would take care of the exponent 2. And the opposite of squaring is square root. So we take the square root of both sides, and we get x equals 4. Now, I actually want to bring this up because it'll certainly be important next year. But we're going to take a look at taking the square root of both sides of an equation. Because it's true that 4 squared is equal to 16, but there's actually another number such that when you square it is equal to 16. Think about it. If you square negative 4 times negative 4 is also equal to 16. So we actually have two answers to this equation here. So that's something to keep in mind, that when you take a square root, you have to consider both a positive and negative answer. Now, in the past, we didn't really consider the negative answer because we were working with Pythagoras, where we were determining lengths of triangles. So we didn't consider a negative length, so we didn't need to consider that solution. Let's move on. Let's now take another nonlinear equation. Say I start with the original expression that I was looking at earlier, x squared minus 6x, but say I make it part of an equation. Say equals 0. We'll keep it as simple as possible. No matter how you try, you realize that you can't isolate the x here. Okay? You know, you could bring the 6x to the other side, but then you've got an x on both sides of the equation. There's no way to isolate the x like we were able to do in the previous example. So that means we have to find another way to solve an equation like this. So this is where now I'm going to have another little aside, and I want you to consider this question. If I have two numbers, and I multiply these two numbers, and they have to be equal to 0, I want you to stop for a second, think about what possible values these numbers could have. So I have a product of two numbers that are equal to 0. What could a and b possibly have as values? So you might even want to stop the video here and think about that for a second. So two numbers multiplied to each other, and they have to be equal to 0. If you think about it for a bit, you realize that the only way this could happen is if either a is 0, b is 0, or they're both equal to 0. So the way in which you can write a solution here is A has to be equal to 0 or B has to equal to 0. There's no other combination that could possibly occur. So if A is 0, regardless of what B is, we know the product's going to be 0. Same thing for B. So what does this have to do with our equation? Well, let's go back. So we realize that we can't isolate the variable easily. So when you're stuck, you just try to do whatever it is you could possibly do. And you know, well, hey, I do know how to factor this expression. So let's see if that's of any help. So we've already factored it before. We know that this thing on the left can be written as x times x minus 6. And that's equal to 0. And this is when we realize, wait a minute, we now have two expressions that are multiplied and it equals to 0. That's exactly what we were talking about earlier. So it's like, say x was our a value and we were multiplying it by the second value b equal to 0. We concluded that one or the other has to be equal to 0. So the only way to find a solution for this equation here is for either the first term to be equal to 0 or the second term to be equal to 0. So either the x has to be equal to 0 or the x minus 6 would have to be equal to 0. Okay, because the product of two numbers equal to 0 means that either one or the other has to be equal to 0. So here x is 0 or x has to be equal to, and if we solve this, bring the 6 to the other side, x is equal to 6. And let's check that these are indeed the solutions to that equation. So 0 squared, 0, minus 6 times 0, also equal to 0. 0 minus 0, yep, that's equal to 0. Let's check the 6 here. Let's do 6 squared. It's 36. Minus 6 times 6, that's also 36. 36 minus 36, that's also equal to 0. So here we see one of the reasons why we need this process of factoring. One thing it does do is it helps us to solve equations where we can't isolate the variable easily. Okay, let's take a look at one more example, and we'll try to put a context to this example here. Okay, so you've got somebody who's kicking a ball, okay? It goes up in the air and then falls back down. Okay, so let's say here's the ground. So somebody kicks the ball, what happens? Goes up into the air, reaches a maximum height, and then touches the ground. Okay, and let's say you have the equation for the height of the ball with respect to time. Now we look at the motion of the ball, we don't expect it to be a linear function, and in fact it isn't, so we'll use this function here. We'll say it's negative 5 t squared plus 25. Whoops, let's say 20t. Doesn't make a difference. Okay, so this is an equation that could represent the height of the ball with respect to time. So we'll say height is in meters and say t is in seconds. The question is here, when is the ball on the ground? Now, hopefully you can answer at least part of this question, because presumably the ball is on the ground when you kick it. So one of our answers should be t equals 0. The ball would be on the ground. Let's give this guy some arms. Okay, as you're kicking it. So really the one that we're interested in is, when does the ball fall back to the ground? How long is it in the air, okay, before it falls back to the ground? So here, if you think about the ground itself, well, that would represent a height of 0. So I can replace h by 0, and lo and behold, what do we have? We have an equation. Okay, in fact, an equation that doesn't look too dissimilar from the one we saw earlier. But again, we have an equation where it's not quite so easy to solve for t explicitly. Okay, so let's do what we did before. Let's try to factor this expression. So we look at these two terms and we realize there's a common factor of 5 and there's a common factor of t. So let's take out the common factor of 5 and the common factor of t, and what are we left with? Well, we take out the 5, we take out one of the t's, so we're left with negative t. And then here we take out a factor of 5, so 20 divided by 5 is 4. And well, we've taken out the factor of t, so no t's left over. And look what we've done. We've written it as the product of two terms, and this product is equal to 0. So as we said before, the only way for that to happen is if the first term is equal to 0 or the second term is equal to 0. But let's solve this here. Well, let's divide both sides by 5. So we get t equals 0. Well, that's as expected. We expect the ball to be on the ground at the time when it's kicked, right at the beginning. And here, if we bring the negative t to the other side, we get t equals 4. That means the next time it hits the ground would be at 4 seconds. Okay? And here we go, another example of where we can use factoring to solve an equation that we were not able to solve using our old methods. Okay, so hopefully this does give you a reasoning as to why we bother to factor. And again, this is something that you'll be taking up again in future years, even as you're taking on more complex functions. Okay, so make sure you learn factoring, and we'll get to some more complex ways of factoring polynomials in the next couple of classes.